we're looking at 5.3, Workplace Apprenticeship 30, Section 5.3, this will be part 1. And we're looking at two things. First of all, we're looking at polygons. And I think we've talked about a polygon before. A polygon is a closed figure. A polygon is a closed figure of 3 or more sides lying on a single plane. So a triangle would be the fewest sides that we could have for a polygon, and that's why this chart down here starts with a triangle, has 3 sides. Okay, and we know this. So a polygon, a closed figure formed by joining 3 or more line segments at their endpoints. All the line segments must lie in the same plane. We talked about this, I think, before. They're classified according to the number of sides. Some common polygons are listed on the table, which you've copied down into your notes. So a triangle has 3 sides. Quadrilateral has 4. A pentagon has 5. A hexagon has 6. A heptagon has 7. And you actually may see, there's another name for this as well, a septagon. Not as common, but you might see that. That also means 7. Hepta and septa are both sort of acceptable words for 7, 7-sided or 7. And then octagon is 8, nonagon is 9, decagon is 10, and then it skips 11 and goes straight to 12, the dodecagon. So there's the decagon and then the dodecagon. Okay, so not every sided figure has a special name. These are just the more common ones. Okay, and there's reasons why we skipped 11 and 12, partly because of symmetry and how they fit together. And how neatly they fit together. The 12-sided is a lot more common. All right, so what is a regular polygon? Well, you might want to take these notes down as well for regular polygon. A regular polygon is a polygon with congruent side lengths and congruent interior angles. Okay, a regular polygon. That means that it's all the same. So a regular triangle would have all the same sides and all of the same interior angles. And we've already got 2 names for this one, don't we? For this triangle right here. So this is an equilateral. You remember that? Equilateral. And it's also equiangular. And now we call it a regular triangle, where all the sides and all the angles are the same as each other. So we can have regular quadrilaterals, regular pentagons, regular decagons, and so on. Okay. This is an interesting shape up here. What kind of shapes do you see here? You see an equilateral? Yeah. Okay, equilateral what? Triangle? Yeah. Equilateral triangle? Okay. Where do you see the equilateral triangle? I see this triangle right here. Is this one you're talking about?
Yes, there's multiple of them.
Okay. That may be equiangular. I would suggest that this angle at the top, I'm going to zoom in there. I would suggest that angle at the top is different than the angles on the sides. What do you think? That angle there that almost looks like a 90-degree angle, and these look definitely maybe more 45-ish. Okay? So I would say this would be probably not a regular triangle. Probably be what kind of triangle? With 2 equal sides. Isosceles, right. Okay. I think I kind of see a square here, right? The square. So that would be a regular quadrilateral, I guess. A square. Regular. All the side lengths the same. All the angles are the same. Okay. Do you see what do you say? Octagon? Maybe, sort of. Are you talking about this right here, like this? One side, 2 sides. Is that what you're talking about?
The inner one.
Talking about the inner one?
The one that's outside the flower.
The one that's outside the flower. Okay, this one right here.
No, the one inside that
one. Okay, well, this is one of them, right? Okay. All right, so that has how many sides? That has 1, 2, 3, 4, 5, 6, 7, 8. Good. That's an octagon. Now this, I thought you were talking about the outside one, which this, with that little dip there, I don't know if that's really we'd call that. So yeah, that one's good, and the one inside as well in the inner frame. It's a bit smaller, but that looks to be a regular octagon as well. Okay. Any other polygons that we see in there? Not even regular ones, but any other polygons like with that you can see with a number of sides?
Hexagon.
You see a hexagon, do you?
Okay, you know where the triangles are? Wow.
Yeah. Up here?
Yeah.
Okay. I like it. 1, 2, 3, 4, 5, and 6. Right. That's not a regular hexagon, but it's got 6 sides. I like it. I like it a lot. So if we zoom in even more, which, you know, we won't go too far in here, but if we zoom in even more, it gets kind of fuzzy, but there are little squares look like here as well, regular quadrilaterals, I guess you could call them. Okay? All right. So that's great. What type of polygons can you identify here? Awesome. Any questions so far? Okay, let's take a look at an example, and I'm going to get you to write this example down. Jot this one down. It says, what are the sizes of the interior angles of a regular hexagon? The sizes of the interior angles, we're going to identify what are interior angles. And of course, a hexagon we know has 6 sides, and regular means that all the sides are the same length. So how might we do that? Well, it would be a good idea to make a sketch of a lot of these problems, okay? Make a sketch if you can, because then you can kind of see what you're looking at. Even if your sketches aren't perfect, it would help to have a little bit of a visual idea of what's going on. So a regular hexagon has 6 sides, and of course probably what you draw first is you draw, you know, the 3 sides up top, and then symmetrically the 3 sides on the bottom, like a honeycomb, right? Again, it doesn't have to be perfect, but you draw something like that. If you want to draw it on its side with the tip up, you could do that too. I don't know, maybe that's easier. It might be a little easier, I don't know. So anyways, all that's good. Now, what are all these other lines for? Well, because it's regular, they put these little hatch marks here, right? To signify that all 6 sides are the same length. Okay. So what are the interior angles? Well, the interior angles would be the angles that are on the inside of where 2 sides meet. So that's an interior angle, and so is that, and this, and so on. Okay? Those are interior angles right here. So interior angles are these gray ones right here. So in this diagram, of course, we're talking about this angle right here. Now it's interesting that they also drew some diagonals, I guess you could call them, from one corner to the opposite corner. So they drew 3 lines that connected opposite vertices. And vertices are the corners, right, where the sides meet. We also call those vertices. A vertex or multiple vertices. So with these lines, notice what we see here. We see that we have 1, 2, 3, 4, 5, 6 triangles. And those triangles are all the same, aren't they? They're all the same. So we have lots of symmetry going on here. What do we notice about the sum of the angles in a triangle? Now follow this logic here, okay? Follow this logic. This is one way that you can look at this. And this might make sense to a lot of you. I'll show you a second way too, but this is the first way. So the sum of the angles in a triangle. Notice, as I said, we have 6 triangles here. So the sum of the angles is 180 degrees. So if we multiply the 6 triangles times 180, what we have is this much. Now that's a very large number. And what that means is this, and I'll just erase some of these lines of mine now. So what that means is this. This angle, and this angle, and this angle, for all 6 triangles. Okay? So, I'll just do this real quick here. Okay? So all of those angles added up is 180, right? Because we have, here's one triangle that has 180 degrees with this angle, and this angle, and times 6. Now, what you notice, or what you might notice, is that the angles on the inside surrounding this center point, those angles would add up to what? 1 full time around a circle, which would be 360. So this, right here, the middle angles are 360 degrees. Doesn't matter what each one is, but we know that all of them are 360. Okay? And so look at what they did. They said, hey, we've got 1,080 degrees minus the 360 from the inside leaves us with 720 degrees on the outside. So all of these outside lines that I'm now erasing, all these outside angles, they all add up to 720. If you take notice that the 720 comes from 6 identical angles, like this, you can divide 720 by 6 to get each interior angle now. See that? So this is 720 degrees divided by 6. So each interior angle is then 120 degrees. All right? Now, do you have to do that every single time with every one? Well, not necessarily, but hopefully that makes a little bit of sense. So I'm going to, before I show you the second way, which is kind of a shortcut, okay? It is kind of a shortcut. What I want to do is I want to just kind of fast forward here. I had planned to do this after I showed you the shortcut, but I'm going to put it all on the same screen, and I'm going to focus down here first on these three. I don't know if you can see all those, but I'm trying to zoom in on a bit. Okay, watch this. Watch this very carefully. So each of these angles in a triangle add up to 180 degrees, right? Okay. Now, if you take a look at a square, which is a polygon now with 4 sides, that's the next largest one. If you draw a single line from one vertex to another vertex that's not connected to the sides that are making that angle, like so you draw across to another vertex, you see that we have how many triangles here now formed? 1, 2. See that? And so what happens here is that this angle and this angle and this angle and this angle is now 180 times 2 because there's 2 triangles there. Okay, which is 360. So the sum of the angles of a triangle are 180 degrees. The sum of the angles of a quadrilateral, 4-sided, have to be 360. What about for a pentagon? This is a pentagon over here. So what I'm going to do is I'm going to make triangles again. There's one triangle I can make. I'm going to now do this. And, oh, that's really bad. Try to go from this vertex to the other vertex. And that's now I've made 3 triangles. Okay? So let's see. If I say there's an angle there, there's an angle there, there's an angle there, that's for the one triangle. For the second triangle, I have these angles. The third triangle, I have these angles. So if we add all of those angles up, I have this one, this one, this one, this one, and this one. So guess what? This one is 180 degrees times 3. What's 180 times 3? Well, that's 540 degrees. 540 degrees. Okay? So, what I'm going to get you to do, okay, what I'm going to get you to do is I'm going to get you to do 2 things. I'm going to get you to draw on your piece of paper, okay, with a ruler. You're going to need a ruler and a protractor. Okay? And I want you to draw a triangle, well, 3-sided polygon, so a triangle. And I want you to draw a hexagon. And I want you to draw a nonagon. 3. And yours is going to be a little different from the rest of your classmates, right? What I want you to do is I want you to find the sum of the interior angles of all of them. For each of them. Okay? So it doesn't have to be a right triangle, it can be any kind of triangle. So use your protractor to find all these angles, add them up, and I want you to check to see if what we've learned so far is actually true. Okay? So take a few moments to do that, and then when you're done, I'll take your answers, and then I'll show you that shortcut formula. Okay, so here's my triangle, and my triangle ended up to be an isosceles triangle here, and I measured with a protractor and confirmed each angle, and then added them up and it got to 180. So that's awesome. Now with the hexagon, so here's my hexagon, and I measured each angle with my protractor. They all should be less than 180. That's the other thing. It has to be not only a polygon, but it has to be a concave polygon. So that means that each angle needs to be less than 180. So if you have a side that kind of like, if they're all going out like this and then one sort of caves in like that, we're going to stay away from those ones. Okay? Well, yeah, technically that can happen. You can have a polygon that has a side that's, an angle that kind of comes in on itself there. Like something like this. This is possible. Something like this, right? Like that, right? But we're going to stay away from these, okay? So it's going to be a concave polygon, not a convex one. We're going to stay away from those. But anyways, so I haven't added up my total here yet, but you're going to add up your total, and we're going to combine our answers when we're done, and we're going to see what patterns emerge, and then we're going to go back to that formula, and just to see if that formula really works. So you guys keep going. With yours, you've got the hexagon and you've got a nonagon as well, one with 9 sides. All right, keep going. All right, so remember when you're using a protractor to make sure that you're looking at the right set of numbers. So if you have an angle that goes like this, and this says, it says 60 on this row, okay, and then 120 on the top row. It's got to be the 120, not the 60, because it goes from here all the way past what would be 90. So it's got to be greater than 90. So you can't use the smaller one always. So you have to be careful how you're measuring that. Okay, so what did you get for the sum of the angles in your triangles? Let's go. I know you guys didn't all get the nonagon done. The sum of your angles were what?
The triangle?
Yep.
59, 59, 62,
Okay, so what's that sum?
180, or
Okay, that sounds like 179. Okay, what was your sum over there?
180.
You got 180?
Yep.
Curtis?
About 180.
Okay, 180.
180.
Okay, so how many triangles are in a triangle? 1. Okay, so it should be 180, probably just half off there on a couple, that's okay. Hexagon, all right, so what was your hexagon? Now, I didn't show you what my sum was, but what were your sums? Hexagon.
I got 180.
You got 180 again, okay?
Oh, I got
Next.
743.
743, okay, that's quite a different.
540.
540
Yes.
and
720.
and 720. Okay, so everybody got something just a little bit. Wow. Okay, so maybe once we get this figured out, reading our protractors correctly, we'll have numbers that are a little bit closer, because those should be like, sorry, 743 and 720 are like in the ballpark, in the same ballpark. So I don't know if those are close to the right answer or not. I'm not really sure. But let's think about it this way, guys. Remember what we did up here. This is super important. A hexagon. If I were to draw a hexagon like this, doesn't have to be a regular one, how many triangles can I make inside a hexagon? How many triangles are there? How many triangles are there? 1, 2, 3, 4. Okay? Now, if I add up all the angles of these triangles, do you see how all of these angles, they actually add up to all the angles in the hexagon? So see, that's one angle, 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 and this is one angle. So all you need to do is think about it as the number of triangles inside. So with a hexagon, we have 4 triangles. A nonagon. Some of you had trouble with the nonagon. I understand. That's 9 sides. Okay. Did anybody actually get a sum for nonagon?
I got 389.
You got 389.
Yeah.
Okay. Anybody else? Did you actually? 480. Okay. Any more? Actually got finished?
Mine's a rough estimate, but
A rough estimate. Okay. No, that's all right. So let's think about this logically now, guys. Listen. A nonagon. What's the pattern? A triangle has one triangle in it. A quadrilateral with 4 sides has 2 triangles in it. Something with 6 sides has 4 triangles in it. Something with 5 sides has 3 triangles in it. So how many triangles would a nonagon? That's 9 sides. How many triangles? 7. Yeah. It would. It would have 7. Okay? So watch this real quick. I'll try and do this real quick. Okay, I'm not going to measure the angles, but 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So if these are vertices, and that's really roughly drawn there, but if these are vertices here, and we draw straight lines from any vertex to any, sort of non-adjacent vertex, I can do this. Okay? Assuming these are straight lines. It's tough to do with a tablet. How many triangles is that? That last one was really bad. So how many triangles do we have here? This is almost artwork here, isn't it? Look at, it's almost artistic. 1, 2, 3, 4, 5, 6, and 7. We have 7 triangles. So guess what? If we add up all of the angles that are in 7 triangles, we should get the sum of the interior angles of a nonagon. So watch this. This is 180 times 3 minus 2. That's 180. This one is 180 times, hexagon has 6 sides. That's 6 minus 2 times 4. And what's that? 180 times 4 is 720.
6 minus 2 or 62?
That's 6 minus 2. No, that's 62. 6 minus 2. What's this one then? 180 times how many triangles are in there? Well, it's got to be 9 minus 2 triangles. So what's 180 times 7? It is 180 times 7?
Oh. 1,260.
1260? Okay, so we're a little off here with those. A little off. But guys, look at, so 720 was correct here. 180, we confirmed that. And most of you didn't finish the nonagon. But here's this little shortcut, and here it is right here. The sum of the interior angles of any polygon, and again it's going to be a concave polygon, is 180 times n minus 2. So please write that down in your notes right now. 180 times n minus 2. So sum of the interior angles of a polygon is 180 times n minus 2. All right. So what I want you to do is I want you to copy down this question before you leave. Don't put your books away yet. Copy down this question before you leave, and then you can go.
Do we have anything?
Here are the remaining questions for this part, 5.3 part 1. There's number 1 and number 2. And then here's number 3. And then we'll start an example 2, part 2 tomorrow.